Chemical reactions and energy. Exothermic and endothermic reactions. Exothermic reactions are reactions where energy is released into the surroundings. This increases the temperature of the surroundings. Endothermic reactions are the opposite. They take in energy from the surroundings, thus lowering the temperature of the surroundings. This energy is given the symbol delta H. So delta H for an exothermic reaction is negative, as heat is lost from the reaction. So the reaction's delta H has been given to the environment, so it's lost heat to the environment, and you feel that as heat, and that's what makes it negative, and it's positive for the opposite, for the endothermic reaction. Melting ice is an example of an endothermic reaction. As heat goes to the ice changes phase from solid to liquid. And thermite explosion is another example I got a picture of here, as it gives energy to the surroundings, heats up. Complete combustion, using methane for example, is also another good example. When an endothermic reaction goes from reactants to products, energy is absorbed, and the opposite is for exothermic reactions. When the reactants become products, energy is released. Here's an energy profile. An energy profile is a diagram that shows what's going on in a reaction, which is between exo and endothermic. Now, as you can see, energy is going up the y-axis, and across the x-axis is the reaction time. It's the pathway of the reaction how it was going. So as you can see, as I explained in the previous slide, the reactants are up here with higher energy. So when they turn to products, energy is released, and that is how the delta H is negative. And for the endothermic energy profile, you can see the opposite is true. It goes up, and energy has to be given to the reaction for the products to be formed. I find this is a lot better for explaining the delta H, how it's negative for exothermic and positive for endothermic, because positive you think the heat is, it can be quite wordy, but I think that is pretty good. Added to this now, there's the same graphs as the last slide, but I've added activation energy, which has the symbol EA. Now, activation energy is the amount of energy the reactants need to get to a transition state. Once they've given this amount of energy, they can turn to products. The reaction is then considered spontaneous, and it carries through. So if you're literally if you're a few kilojoules of energy too low, it won't happen. But the second you hit that kilojoule marker for the energy, the reactants turn to this transition state, then quickly go down to products. As you can see, this goes, and it's the same for endothermic. But the activation energy is a lot higher because you have to give more energy to get to the transition state to become products. Bond energy is the amount of energy in the bonds of the reactants and products. So I've got an example here. These numbers are made up by me just to explain the process. It's not the actual energies for these. You can look them up if you wish, or whatever. We've got the complete combustion of methane here. So on the reactant side, you've got methane and oxygen going to carbon dioxide and water for the product. So methane has 4 single carbon-hydrogen bonds. So if we look over our bond energy graph, we see that's 233. So it's 233 times 4. This gives you 932 kilojoules. Oxygen has 1 double bond between the two oxygens. So it's 1 times 426. It's 426. So the total bond energy is then both added together, which gives 1,394 kilojoules. Do the same for the products. Carbon dioxide has 2 CO bonds, so it's 420 times 2, 840 kilojoules. Water has 2 OH bonds, single bonds, so it goes 2 times 401, 802 kilojoules. Total is them added together, 1642. The overall energy of the reaction the overall bond energy of the reaction, is the reactants minus the products. So we've got 1394 minus 1642 equals minus 248 kilojoules. So from this, we know it's exothermic because the overall delta H, the overall energy, is a minus number. If this was positive, it'd be an endothermic reaction. So, if you want to pause, I've got these, maybe go through it. Should be quite fresh in your mind if you just watched it. But I'm going to go through it now. Okay. Ammonia is manufactured from hydrogen and nitrogen in the Haber process. The equation shows the bonds which are broken and the bonds which are formed during the manufacturing of ammonia. So 3 hydrogens and 1 nitrogen goes to 2 ammonia molecules. The relevant bond energies are shown in the table above. These are here. Calculate the total energy needed to break all the bonds in the hydrogen molecules and the nitrogen molecule. Okay, so you have 3 hydrogen single bonds, so 436 times 3, that gives you 1308. Then you have 1 nitrogen triple bond, which is 945, give us the total of 2253 kilojoules, so 2253 kilojoules. Calculate the total energy released when all the bonds in the ammonia molecules are formed. So we've got 6 nitrogen to hydrogen single bonds. That's 391 times 6, which is 2346 kilojoules. We do reactants minus products, 2253 minus 2346, and we get minus 93 kilojoules. Once again, pause if you want a quick go through this or have a look at this. I'm ready to go. Now, so the manufacture of ammonia is an exothermic reaction. Select the graph below that matches the energy profile diagram of an exothermic reaction. Well, as we know, the reactants will be higher than the products in energy because the overall delta H will be negative. So the answer is A.